All right, 811 and 812, volume using the washer method. So the good news is this is really the same. We are just cutting out a part of whatever thing we are finding the volume of. Thus, we are creating a washer. So if you think about what a washer is, I don't know what they're used for, but they're these not 3D. I mean, they are 3D, but they're these like donuts, right? And that's what we're doing. We're finding the volume of a donut because we're gonna cut out this inner volume. So let's consider what this will look like. If I've got horizontal axis of revolution, so let's say I've got this function and maybe this function. We'll notice that they intersect right here, so that's going to be my B, and we'll say A is our y-axis. This is the area we are revolving, but to find this, we are going to need this big radius. I'm going to call this capital R of x, and we need this smaller radius. So this is going to be lowercase r of x. And we're going to take that entire big radius circle area and then subtract from it the little radius circle area. That means the volume of this will be pi times the integral from a to b of our big radius r of x squared minus our little radius r of x squared dx. Because really, I mean, if you think about it, you could distribute that pi in. You're taking the area of the big circle, all of those circles, and then subtracting from it all of the areas of the little circles. What if we have a vertical axis of revolution? Well, it's going to be very, very similar. So let's say we've got here a function, and we'll draw the same kind of two functions. Here a function, but in this case, we are rotating this region around our y-axis. And so we've got, again, big radius, so I'll say capital R of y, and little radius, lowercase r of y. And again, we have our bounds. We will name them, instead of a and b, we'll say this is c and d. So the volume here would be, I think I need to move things, pi times the integral from c to d of our big radius r of y squared minus our little radius r of y squared with respect to y. It's kind of combining the things we did most recently with our area using, or finding the area where we had two functions, like any of these really, but where we took the upper minus the lower. It's the same idea. So let's do one together. Find the volume of the solid formed by revolving the region bounded by the graphs of the square root of x and x squared about the x-axis. Sketch the graph and draw a representative rectangle. All right, so the square root of x, well, I know that that's 0, 0, and I know it has 1, 1, and I know the general shape looks like this. Close enough. I also know x squared is a parabola. It goes through 0, 0 and 1, 1, but we know it kind of has that upward curve, and let's see if I can draw this. It's kind of hard. All right, there's our x squared. X squared, square root of x. All right, that means this is the region we are rotating, and we are rotating around the x-axis. So let's consider our figure here. A representative rectangle, well, we're taking this big radius. Oops, I should have maybe moved it over r of x. That didn't really help much. Minus this smaller radius, So I am looking at pi times the integral from 0 to 1, bounds 0 where they intersect, 1 where they intersect. The bigger radius is the upper one. So in this case, we're looking at the square root of x squared minus, and our littler radius here, the one that's lower, is our x squared. X squared squared with respect to x, right? Pi r squared. So to evaluate this, I'm going to simplify a little first. Pi times the integral from 0 to 1 of x minus x to the fourth, pi times 1/2 x squared minus 1/5 x to the fifth, and we are evaluating from 0 to 1. Because we have that 0 lower bound and both these pieces have x's, I don't need to worry about that, so I really have pi times the quantity 1/2 minus 1/5, and I'll do this algebra. Pi times 5/10 minus 2/10 is equal to 3 pi over 10. 3 pi over 10 is the volume of this weird donut-esque, well, it's not really donut-esque, but if I took this region and rotated it around that x-axis. We got another case. Find the volume of the solid formed by revolving the region bounded by the graphs of, all right, let's start. X squared plus 1. So I know that it's a parabola that's opening up, that's moved up to 1. So I'm going to go over, up 1. Here's what I got. Y equals x squared plus 1. The line y equals 0. So that's our x-axis. The line x equals 0, y-axis, and x equals 1. So this is our region, and we are revolving this region about the y-axis. So we're going around this way. So let's think about it for a second, because what's kind of important about this problem is notice as I go from, so we're going around the y-axis, so I'm going low to high, right? I'm going, these are my rectangles. Up until this point right here, I really only have one function to worry about, specifically the line x equals 1. So I'm going to take that into consideration by setting up two integrals, right? I really only need to consider this graph, x squared plus 1, once we get to 1. So my first integral is from 0 to 1. And if I want to find the area of this little circle here, it's going to be pi times this radius, which is a radius of 1, squared. And because we're doing this with respect to the y-axis, I am looking at dy here. But that is just this first piece. I've gotten like this area right here, this volume, once we rotate it around, taken care of. Then I have this little guy I got to deal with. So I'm going to pause this. All right, I just need to make that little integral a little smaller. So to this, we are going to add, I know it's going to be an integral from 1 to 2. I know I need that pi out front, but now let's consider what this is going to be. The big radius, let's say r of y, this is a radius of 1. The little radius, lowercase r of y, is this small distance. So actually, I need to solve for x here. So I'm going to subtract 1. X squared is equal to y minus 1. X is equal to the square root of y minus 1. Now, technically it's positive or negative, but because I'm looking at the version that is to the right of our x-axis, I'm looking at the positive piece, so I can keep it as just that positive. So I have big radius squared, 1 squared, minus little radius squared, the square root of y minus 1 squared with respect to y. And now I can evaluate. I've set it up in two pieces. For this first one, 1 squared is just 1. The antiderivative of 1 would just be y. I have pi times y evaluated from 0 to 1. We'll get there in a moment. For this little guy, I'm actually going to simplify it first. So we have pi times the integral from 1 to 2 of 1 minus y minus 1 dy, or pi times the integral from 1 to 2. 1 minus a negative 1 is really 2 minus y dy. Coming back to this, we'll plug in our value. 1 minus 0 is 1. So this is really just pi times 1. This first guy is just pi. Down here, okay, so we got pi that's coming along for the ride plus pi times the quantity 2y minus 1/2 y squared evaluated from 1 to 2. And we plug in all of our values. All right, pi plus pi times, first we plug in 2. 2 times 2 minus 1/2, 2 squared, minus, and then we plug in our lower bound, 2 times 1 minus 1/2 times 1 squared. And I take some time to actually evaluate this. 2 times 2 is 4, and then 4 minus 2 is 2. And then we've got 2 minus 1/2, which is 1/2. And we still have that pi out front. Oh my goodness. Then we have pi plus 2 minus 1.5 is 0.5. Pi plus 1/2 pi is 3 pi over 2 for my final volume. Technically, from here, we could type that into our calculators. I really just went through that work because it's good practice. All right, for our last 3 examples, we're going to set them up, but then you can use your calculator to solve. Find the volume of the solid formed by revolving the region bounded by the graphs of, so we've got y equals x squared plus 1, y equals 0, x equals 0, and x equals 1. So this is the region we are looking at, and we are rotating this about the line x equals -1. Ooh, interesting. We are rotating this around this line right here. Shade the region being revolved, draw the axis of revolution, okay, we did those 2 things, and draw representative rectangles for big radius and little radius. Okay, so it's the same issue we came across last time where we need to do 2 different integrals because this first part from 0 to 1 only deals with this right here, and then the second piece from 1 to 2 also has the parabola involved. So let's just consider this first part, the integral from 0 to 1. I'm going to throw the pi out front because I know I need that. So what is our big radius here? Well, let's think about it. This distance from the y-axis to the line x equals 1 is a distance of 1. This distance right here is also a distance of 1. So this whole radius is 2. And then the little radius, even though it is from, well, I guess we could think of it as from 0 minus a -1, this has a small radius, r of y is equal to 1. So this first part here, this first volume, is big radius, 2 squared, minus little radius, 1 squared, and this is with respect to y. We then need to add to that the other piece here. I'm going to clean this up a little. All right, here's what I know. I know I need the pi. I know I'm going from 1 to 2. That's kind of the easy part of the setup. Now let's consider what our radii are. I know that I'm doing this with respect to y, so I need to change this into what we had before, the square root of y minus 1, and I know I need only the positive version because I'm only looking from the positive side of our y and x axis. But if I think about what this whole radius is, let's take the big R of y. It's that same thing we had before. This whole radius, let's say even, I'm going to move this so you can see it, all the way to the line x equals 1. Well, this radius is 2, and that's not changing, right? This whole radius is 2 all the way along. The little radius is the one we need to think about. Lowercase r of y is the thing we need to consider. So this distance right here from the y-axis to the curve is the square root of y minus 1. But then we have to add on to it this distance of 1. So the entire small radius would be the square root of y minus 1 plus 1. It's whatever this distance is plus this distance of 1. All right, that helps us then, because the volume of this region from 1 to 2 then is big radius squared, 2 squared, minus little radius squared, minus the square root of y minus 1 plus 1 quantity squared, and of course this is all with respect to y. Now, we can do this by hand, or from here we can go to our calculators. I would probably suggest doing this by hand, right? 2 squared is 4, minus 1 is 3, so we have the integral from 0 to 1 of 3. You guys know how to do that one. In this, maybe you could simplify a little bit before you plugged it into your calculator, specifically maybe putting this as 4, but you could really just do the integral from 1 to 2 of 4 minus the square root of y minus 1 plus 1 squared dy. I would also urge you to calculate this integral as a value, as a number, and then put on a pi at the end. Don't plug your pi into your calculator because that will give you a decimal approximation, and that's not super good. So take some time right now, pause the video if you want, calculate this. I got 25 pi over 6. Right? We're going to set up this integral again, and you can solve it in your calculators. Same curves, y equals x squared plus 1, y equals 0, x equals 0, and x equals 1. And here's our region. In this problem, they say, let's rotate it about the line y equals negative 2. So y equals negative 2 is all the way down here. We are rotating this around. All right, so I can tell you right off the bat, we need our pi times r squared. And our bounds, because we are rotating it around our y equals negative 2, are going to be from 0 to 1. And now let's think about this. What is our big radius here? The big radius, let me do it with red. Capital R of x is equal to, well, it's that x squared plus 1. It's this distance, but then we have to add on this extra little bit right here, plus 2. So our big radius is x squared plus 3. Big radius squared minus the little radius squared. So in this case, our little radius is this distance right here, which is a distance of 2. And so our little radius squared would be 2 squared, which is 4. And this is all with respect to x. If you would like to evaluate that by hand, you definitely could. Otherwise, take some time, type it into your calculator. I got 36 pi over 5. One more. Same regions. X squared plus 1. X equals 0. X equals 1. Y equals 0. Here is our region again. What if we take this and we rotate it about the line x equals 2? Ooh, interesting. So we're going around this way. Once again, we have that scenario where the integral from 0 to 1 is going to be different than the integral from 1 to 2. So let's focus on the integral from 0 to 1 first. We need the pi. What is our big radius here? This is a total distance of 2. 2 squared minus the little radius here, total distance of 1. 1 squared. And it's with respect to y. Then we have this other integral from 1 to 2. We're going to add in that pi, 1 to 2. All right, what is our big radius here? This radius would be the square root of y minus 1. We've seen that a couple times. But then I have to add to it. Oh, no. I'm sorry. I said, oh, no, because I was thinking about it wrong. Okay, I am going to draw a picture over here, I think, to make it super clear. So this distance is the square root of y minus 1, this x distance. If I want to figure out what this distance is, this is my question mark, I want to take my entire length here and subtract from it that red. Well, the entire length is 2, so the green would be 2 minus the square root of y minus 1. That is our big radius here, r of y. Little radius is, I don't have enough room. Little r of y is just that length of 1. So minus 1 squared dy. And I would probably simplify that a little bit before I went and typed it all into my calculator. But when you do, you should get 23 pi over 6. Sorry that I kind of had a little mess up earlier, but I think we're okay. And sorry that was a bit of a longer video, but it is what it is. Okay, have a good day.